Okay, so now we'll review the problem of finding the volume of the solid that lies within two spheres. This is problem 7 in section 10.1's WebAssign homework. So we're given two spheres, this one and this one. Of course, the one on the left is already in a nice standard form. The one on the right is going to need to be put in standard form. We do that by completing the square, and we end up with this equation right here. So with an equation of a sphere in standard form, we can find the center and the radius of that sphere now. We have -2, +2, -1, radius will be 2. These things are listed below. -2, 2, -1, radius is 2. Our center is 0, 0, 0, and r equals 2 for our first sphere's equation. So now we've got full information on each of these spheres. It's kind of the easy part. It's the obvious step to take is to find the center of both and the radius of both. Something we'll notice that should be useful is the radius of each of these spheres is 2. So they have a matching radius. This might make life easier, and in fact it will, but we suspect that from now without even knowing it. Now, since we don't have anything else to do in this problem, we don't have many tools in chapter 10 at this point, and basically only tools from the past to use. Let's just do the only thing we really have from this section. We'll look at these two centers and then find the distance between these centers. Right? Use the distance formula, and we'll see that the distance between the two centers is 3. Okay. So the distance of 3 between the two centers, it's a nice whole number distance. It kind of begs us to draw, or at least sketch, what the geometry of this problem looks like. Now, one thing I would encourage is don't try to sketch this sphere exactly where it is in a three-dimensional coordinate system. That's just going to be difficult, right? We can use the distance between these two spheres. The fact that they have the same radius tells us that they have the same shapes. So we can just really get a cross-sectional view of these two spheres' intersections. And that's what I've got right here. This is the two-dimensional view of the intersection of these two spheres, these two three-dimensional spheres. So just to zoom in a little bit. And the way I've drawn it is not to try to figure out where they are in 3 dimensions and really work on a plane that passes through these two. But of course, yes, there is a plane represented right here that passes through these two spheres. We don't have the tools to establish the equation of that plane yet. So there must be a simpler way through this. In fact, there is. So the way I've drawn these two circles, or two spheres in profile, just looking at them slicing as a slice, is to mark off 1, 2, 3. These 4 points are unit distances apart. So stepping from this center of circle 1, we'll step 1, 2 units is the outside edge of that sphere or circle in profile. Going the other way, we've got 1, 2 units to represent the radius of the other sphere in profile. Now, in between is this line right here. Okay, so halfway between these, well, if we needed to really calculate that, we'd realize that these two centers are 3 units apart. Halfway between them is a distance of 1.5. So what we know now is that this line here is actually 1.5 units away from each center. And what we're looking for then is the volume of the end cap of a sphere when this flat portion here, is at the point 1.5 units, its center point is 1.5 units away from the center of the sphere, and we're looking at the volume of the rest of the end cap this way. Okay, so to clean that up again, we'll see the picture drawn off to the side. We're just looking at the volume of a piece like this. Okay, and so that's only half of them, that's one end cap, but since they're symmetric, the two spheres both have radius 2, then we'll just double the volume that we find here to get the total volume. So how do we find the volume of the end cap of a sphere? Well, we'll have to remember Calc 2. We'll go back to Calc 2 techniques, volume of a solid of revolution, that's step 5, and we'll calculate the volume of that end cap. So what I've done now is just taken one circle, that we're going to rotate about, I don't know, it doesn't really matter whatever axis we rotate this circle about, but maybe we'll say this axis, the x-axis. Okay, that'll form a sphere. If we look at just this line right here, that'll form the end cap that we're interested in. And from what follows this way, we're just going to use the disk method for the volume of a solid of revolution, and it's just essentially Calc 2 techniques. Remember that the radius at any given point is given by this little segment here. If we're looking at cross-sectional areas of these disks, the area is going to be A equals pi r squared. Remember that the volume formula tells us that we're going to need to use V equals A to B, some limits of integration, A of x dx, and that's how we sum up all the areas times their infinitesimal widths dx to get the volume of this solid of revolution for this end cap. Now, some things we know about this. We know that r is the same thing as y. R is the same value as y. So that's, if we just look at the picture, yeah, this is our xy coordinate on any one of these. This is an xy coordinate that's on this circle, y equals square root of 4 minus x squared, just to represent that circle in a handy way, not x squared plus y squared equals 4, which is also true. And we know that the area is pi r squared, so then this is pi y squared, since r and y are the same, but we're not going to integrate with y with respect to x, so we need to change that. Y is equal to 4 minus x squared, and we end up with, this is our expression for the a of x area function. Okay, our limits of integration are fairly obvious. This is that point 1.5 or 3 halves, and then we'll integrate up to 2. Find this volume right here, double that, and we've got the total volume for this. So this problem involves quite a bit of Calc 2. It wasn't my intention to have something so wandery through old material. I'll try to avoid stuff like this in the future, but it is, in the end, kind of a nice problem that uses a lot of tools. So good luck with it, and see you in the next video.